Hi friends, a very good evening. Could you please confirm in the chat window if you're able to see my screen and if you're able to hear my voice? That will be very helpful and I know that things are working well. Could you please confirm in the chat window please if you're able to hear my voice clearly and if you're able to see my screen? We'll get started with the session in a couple of minutes. Anyway, I think some of our teammates, including me, have been answering some of the questions in the chat window for the last 4 or 5 minutes. Okay, good. Okay, good. So no glitches, which is good to know. Okay, good. So I can also see my live session. Yeah, everything is clear. Thank you, mentors, and thanks everyone who has confirmed it. Again, Rajesh is requesting to do a general Q&A session. We're planning to do it next week, tentatively. Right, so we wanted to finish this session and mostly we have one more session for COA on Saturday. Today is Thursday, right? We had to move it slightly because I had a small glitch with my home internet connection yesterday, so hence I had to take I couldn't go live yesterday. So today and Saturday are our live sessions for COA. Once that is done, we'll do a general live session and start with DLD. The DLD content is uploaded as requested by students. I've redone it with the help of my whole team, and please check out the content. And we'll be doing lots of more problems for DLD as part of the live sessions, and we'll add it back to the course videos, right? Again, somebody seems to have a problem finding English. It's been done even last year, so it's already available in the course videos. If you are not able to find it, please feel free to call us or email us, right? Okay, sounds good. Cool. Let's get started, guys. It's anyway 7 p.m. So let's get started with each of our questions. And my suggestion for you would be to focus on the answers, because our objective, the reason we all are here today, is to solve these problems. Any general questions you have, feel free to go to our website, which is gate.appliedcourse.com. Email us at gatecsc@appliedcourse.com or call us here. We'll try to answer as many questions as possible. Right? So back to our discussion for today. Let's get started. This is COA session 2. Okay, cool. Okay, here comes the first problem. We are going to start with some easy problems and go to slightly more, not even hard, medium level problems by gate standard. We're going to start with some simple problems. Again, this is a fairly straightforward problem about having a special processor. Okay, I'm also looking at your answers in the chat window. As and when I see some problems, as and when I see that enough number of you have answered there, I'll go ahead and solve the problem for the benefit of others. Again, as mentioned by our mentors also in the chat window, please focus on solving the problems, because this is what will get you a gate rank. General questions, you are free to ask us, shoot us email, and shoot us an email, we'll help you, or call us, we'll try to answer as many calls as we can. Focus on the task, please. We are here to solve problems. Please focus on it. Do your best. Okay, I see a bunch of you putting in your answers. Good. Okay, I see slight variation in the answers. Again, it is possible to make silly mistakes on this problem, but this is a fairly straightforward. You just have to apply a formula here, if you know what formula to apply. I'll wait for a few of you to answer, then I'll go and explain the solution itself, as we often do, as we always do actually. Okay, let's wait for a few more seconds. It'll take some time to warm up, right? There are a few lengthy questions also, so I'll give more time for those questions for sure. There are a couple of lengthy questions that you could be asked in GATE for 2 marks. This is a simple question. Yeah. So most of you got it right. Thankfully, it's a straightforward problem. The answer here is C. And again, all you have to do is you have to just apply Amdahl's law. I hope this is the spelling, right? Amdahl's law, right? This is just about applying Amdahl's law. What does Amdahl's law? For speed up says the overall speed up, again, you can derive Amdahl's law. It's a very simple law to derive. Even if you have forgotten it, you can derive it. It's very simple. Okay, what it says here is the overall speed up that you'll get is 1 by 1 minus, so F here is the fraction of operations for which you can speed up, right? Plus F by S. Okay, F is a fraction of operations on which you have a speed up of S. 1 minus F is a fraction of operations on which you don't have a speed up. Okay, this is your Amdahl's law. Again, this is very simple law to derive. It's again, you don't have to remember this. It's fairly simple to derive, but since we know this, it will make it faster. Our speed up is 15, and it says on 50%, which means your F is 50%, your S is 15. So what you have here is 1 by, this is 0.5, 1 minus F is also 0.5 here. This is 0.5 plus 0.5 by 15, which will make it 1 by 0.5 plus 0.33. This is this is 0.5 by, this is 15, right? Yeah, so this is 0.3333, right? So this whole thing is 1 by 0.833, and if you just use a calculator, this is equal to 1.87, right? You just have to apply Amdahl's law. That's it. Again, if I'm not a big fan of remembering formula, but you can derive this also. Just in the interest of time, I'm assuming that you guys know how to derive it from first principles and you've learned it. If you're a course registered student, obviously we discussed it in the course. If you're not a course registered student, this is fairly quick to understand and derive also. Cool. So let's go here. Let's go here. Oh, so did I make a mistake somewhere? One second. I think I made a mistake. Sorry. Okay, so this is 0.5 by 15 is okay, sorry, my bad. Okay, sorry, my bad. I think I made a small mistake here. Let's use a calculator, right, just to be sure. 0.5 by 15. 1 second. 0.5 by 15 is 0.033. Yeah, just wanted to make sure. Sorry, my bad. 0.033. Thank you for the correction. Somebody mentioned this, right? Sorry. So this is what it should be. Again, let's use the calculator. 1 by 0.533. So 1 by 0.533. 1 by 0.533. What is happening here? 1. Somehow my 1 button is not working on my. Okay, so let me get my calculator out. So 1 divided by 0.5333 is 1.87. I'm sorry. Yeah, I made a small mistake here. So I wrote this by mistake as so 0.5 by 15 is 0.033, not 0.33. My bad. Okay. So yeah, I should have used a calculator myself while solving this. Okay. But thanks for the correction. I think somebody made this correction, right? Let me see who it was. Keshav, thank you very much for the correction. I think you found that. So yeah, so that's what it is. Somebody has a problem with the voice. Let me check what is the problem with the voice. Okay, I'm increasing the audio output. So in case you have your earphones or speaker at full, you might want to reduce it. I've just increased the audio output just in case you have a problem, right? Okay, sounds good. So this is cool. Yeah. So that was a silly mistake on my part, but thankfully we got it resolved with the help of one of our students. Cool. So let's go to the second question now. Okay, here comes the second question. Okay, I hope the voice is clearer enough. Again, I just set it little low to avoid the background noise being caught up. Cool. Let's go to the second question now. This is also a fairly easy question. If you know how to understand the dependencies between instructions, this is fairly straightforward. Okay. Again, this is fairly straightforward. If you know how to read some COA instructions, this is fairly straightforward. Just be careful here. Please read the instructions carefully. You have load followed by a couple of arithmetic and logical, then a store. Right? You have 6 instructions in total. So please be careful here. This is very easy to make a mistake on. I see some of you already making a mistake. So, okay, I'll just leave some space so that you can see it more clearly. Again, we make weekly announcements of our live sessions. So we make them well in advance. For example, for COA, we made the announcement almost a couple of weeks back, if I'm not wrong. And after COA is over this week, next week is DLD. So we make those announcements well in advance so that you can revise and come for these sessions. Okay, I see a varied spectrum of answers from 3, 4, 5, 6. Just think little carefully. Look at how many data dependencies are there in these instructions. Again, I see somebody also has an option of 9. So there is 3, 4, 5, 6, 9. Okay, quite a range of values. These are raw data dependencies that we're talking about. Okay, let's see what this is. So let's go into this, right? So let's solve this. Since there's a wide spectrum of answers, I thought it's best to answer this. So instruction 1 is a load instruction with no dependencies. You're storing based on whatever is there in this S1, and of course this is like the memory location of 0 plus whatever is stored in S1 to S2. There is no dependency here, right? Now what about the second instruction? Second instruction, you're loading some data into S1 using S6 and 40. 40 is a constant here, like it's like an indexing. Now what about S3? S3 uses, if you look carefully, S3 uses S1 and S2, right? So, sorry, instruction 3, I'm sorry. This is instruction 1, instruction 2, 3, 4, 5, 6, right? So instruction 3, if you notice, instruction 3 is dependent on instruction 2 because it gets S1 from there. Instruction 3 is also dependent on S2 from 1. So there are 2 dependencies here. It is dependent on, so instruction 3 is dependent on instruction 2. It is also dependent on instruction 1 for S1 and S2. Right? So there are 2 dependencies there. What about 4? What are the dependencies of 4? Look at this. 4 requires S2. Look at this. 4 requires S2. Right? Again, this is an add where S2 is added to S2 and the result is stored in S6. Right? This is how this operation, the 3 address add operation looks like, right? So you have S2. So I4 depends on S2, which means I4 depends on 1. So there is 1 dependency here. 1 data dependency. That's what we're talking about, right? Now what about 5? 5 requires S6. Right? 5 requires S6. Okay, so okay, so this is an OR, right? So this $0 is basically, okay, so this should have been S0. I think there is a small typo here. This is $S0. S0 is not there anywhere, but your instruction 5 requires S6 to be present, and S6 it can get. Look at this. Instruction 6 is dependent on what all stuff? Instruction 6 is dependent on S4, right? Because after this instruction, it is executing this S6, this output that is stored in S6 has to come here, right? That's important, right? So 5 is dependent on 4's output. So there is 1 dependency there. What about 6? Okay, so 2, 3, 4, right? What about 6? 6 requires S1. Okay, where is this S1 coming from? S1 is coming from instruction 2, right? So there is one dependency there. Are there any other dependencies? It also requires, look at this, it says store the result in S6, but this S6 value itself comes from 4, right? This S6 value itself comes from 4, right? So you require one more here. So 2, 3, 4, 5, 6. So there are a total of 6 dependencies in this case. Again, you just have to look at for every instruction what it is dependent on in the prior stuff. So there are a total of 6 raw data dependencies in these instructions. If we are a little careful, it's fairly straightforward to answer this, right? Cool. Next, now again, some of you may think that here you don't need it. Some of you may think the answer is 5, but read the statement here. It says whatever is there in S6 is stored to this memory location. So for S6, right? Look at this. Some people may think here there is no data dependency, but this S6 that is S6 which is the output. These two are added and the output is stored here, right? That S6 is what you have to store here. So this S6 is dependent on, or this instruction 6 is dependent on instruction 4. So if you look carefully and read this document, read whatever is given here carefully, you can easily recognize that there are 6 data dependencies in this, right? So let's go to the third question. Again, this is an easy question. If you're careful, it's very easy to make silly mistakes on this. So you have to be slightly careful here. Okay, cool. Let's go to the next problem. This is also a fairly straightforward and easy problem. Again, for some of the questions that are asked about the previous question, I answered them. Others, in case our mentors will try to answer some of those questions. If they're not answered in the chat window, feel free to email us. I know that in the 6th instruction in the previous question, people would get confused. Okay, it's a slightly tricky question, so you have to be slightly careful there. Okay, this is about simple pipelining. This is a fairly simple question. If you know about how pipelining works, this is straightforward. Okay, people are putting in their answers A, C, D. Okay. Again, we are starting with easy questions. We'll go to slightly more interesting questions little later. There are a couple of lengthy questions also, which will take you time, and I'll give you ample time to solve those. Again, this is a very straightforward question about pipelining. So somebody is asking, in GATE, will it be clearly mentioned that a question is MSQ? Yes, don't worry about it. The examiner, whoever sets the question paper, will clearly indicate if a question is MSQ. In today's session, I don't think there are any MSQs, but in the previous couple of sessions, we had MSQs, and we'll start adding more and more MSQs in the future sessions. Okay, so yeah, most of you got it right. So let's go into the solution. This is a fairly straightforward thing, right? So let's look at the non-pipelined process first. Right, so let's look at the non-pipelined and the pipelined, right? So there are two things here, right? So what is the execution time for the non-pipelined processor? The non-pipelined processor, with all the information that you have, the cycle time is 20 nanoseconds and the cycles per instruction is 1.4. So the total execution time is 20 cross 1.4. This is 28 nanoseconds, right? So this is the total execution time in the non-pipelined processor. In the pipelined processor, let's see what happens. It's a 5-stage pipeline. Each stage takes this much, right? So now what is the question? The question is all about the best case speed up, right? So what is the execution time now? What is the execution time now? So you take the maximum amongst 2, 3, 8, 6, 1. Because one of the stages that you have in the pipeline takes the most amount of time, right? So that's the bottleneck literally for your whole pipelining. So take the max of all of them, which is 8, multiply it by, it also says something here, right? Assume that the average CPI for the pipeline processor is 1. So the cycles per instruction is 1, right? So you have a 5-stage pipeline. So you take the max of all of them. So you get 8 nanoseconds as the execution time for your pipeline processor. So now what is the speed up here? It's 28 by 8. Let me be careful. So 24.5. Yeah. So 3.5 is the answer here. I'm a little careful from the time I made that silly mistake of 0.5 by 15. Okay. I want to be real careful from now on. Okay. I'll use a calculator if I have to. Okay, cool. It's a very simple problem. Let's go to a more interesting problem. This is an interesting problem. It's not hard, but this is interesting. Again, this might take a little more time to solve. Please read the question carefully and draw the diagram. It's okay if it takes time. It's perfectly okay. But please take time and solve this. That is extremely, extremely important here. It's okay if it, again, this is a slightly lengthy question. We know this, right? Please read the question very, very carefully. It's okay. This will take time. Please draw the whole diagram, that whole matrix very, very carefully and solve it. You can encounter questions like these for 2 marks in GATE. Actually, they have been asked in the past. Again, we are trying to start with easy questions, but also expose you to slightly medium level questions. There is no benefit in only doing easy questions. There is no benefit in it. That's why we started off with very simple questions. The last 3 questions that you saw were very simple. This is not hard. This is lengthy. That's it. Doing trivial questions will not get you a GATE rank. These are easy and medium by GATE standard, not by my standard or your standard. Okay, I see people putting in the answers. Okay, I see some variability in the answers that students are putting in. That's okay. Just check your answers carefully. That's all you have to do thoroughly. See if various stages can overlap or not. Again, remember, I'm just reminding you, there is no forwarding here. Okay, there is no forwarding here. And it also says that ID and WB may share the same cycle for dependencies. Again, since there is so much variability in answers, please check your answers once. Just check your answers. Be careful. Remember, there is no forwarding here. There are 5 stages. There are 6 instructions. Also, look for dependencies. That's a very common mistake that people commit when solving problems like these. Typically in GATE, similar problems have been asked. They are easy, but they are time taking. That's the only catch. They're not hard actually. If you think carefully, they're easy. Okay, a good chunk of you have put in your answers. So let me show you the solution, right? So I have drawn this diagram just in the interest of time. I've already drawn this diagram and put it here, right? So this is the whole solution. Okay, so let's go step by step. My team helped me in drawing this whole solution. So this is your instruction 1, instruction 2, instruction 3, 4, 5 and 6. Let's start with instruction 1. Okay, so the answer here is 16 by the way. Okay, but let's go step by step and understand it. Instruction 1 has 5 stages: fetch, decode, execute, your memory operation, and then the write operation, right? So 5. Now second instruction, look at this. There is no dependency between the first and second instruction. So the second instruction can go into the fetch as soon as the first instruction goes into the decode, right? So here it goes into, so your I1 occupies the first 5 slots, your I2 occupies these 5 slots. These two are the simple things to figure out. It is I3 where things get slightly more interesting. Look at this. I3 requires, so this is an OR operation, right? This is an OR operation on R1 and R2 and the result will be stored in R1, right? So it requires R1 from here. So I3, look at this, that's what we have written. I2 and I3 are dependent instructions. So I3 must wait for all the operands. I3 must wait for this operand before it proceeds, right? When do you get this operand? Look at this. So it can fetch, see, I3's fetch can happen immediately. As soon as I2 goes into decode stage, I3's fetch can happen. But I3 can't decode because R1 is not available yet. Because this R1, this register 1, we are dependent on the output of instruction 2. Instruction 2 has to perform this AND operation and store the result here. And it does this in the write stage. Look at this. So again, remember there is no operand forwarding here. If you notice that's why I mentioned this. Okay, so that's why I mentioned here. There is no forwarding here. There is no forwarding whatsoever. That's why I called that out very clearly, right? So I1 is done, I2 is done. When it comes to I3, I3's fetch can happen here, but I3's decode can't happen, right? So here I3 doesn't do anything, here I3 doesn't do anything. This is the important thing. As soon as I2 writes it back, then this decoding can happen, right? So this is the most important thing here. Now after D you have E, M, W, all this is okay. So I3 is done. Now I4's fetch will happen only after I3 goes into decode. So I4 also you can write these 5 stages like this. Now let's look at I5. This is 1, 2, 3, 4 and 5. Now if you notice carefully, this requires R2 and R1. This R2 is dependent on this. So I5 is dependent on I4. Right? Look at this. I5 is dependent on I4, just like I3 was dependent on I2. Same logic. So that's why even I5 can fetch the instruction, but can't decode it till this time. Same reasoning, because there is no forwarding here. Right? That's the important part here. Okay. So next, you have I6. This I6, whatever is there in R3, it is stored here. Whatever is there in R3, it is stored in this memory location. This is like an indexed addressing here, right? But for this R3, we have to wait for instruction 5 to finish because instruction 5 outputs R3. So even instruction I6, we can fetch it here, but we can't decode till this point of time. right? So if you write this carefully, again, remember, these two will be blank, these two will be blank, these two will be blank, because there is no operand forwarding and there is a dependency. So this question is all about recognizing the dependency and figuring out that these spaces have to be empty. And if you fill it, it will take a total of 16 cycles to get the answer, right? Or it requires a total of 16 time steps or 16 cycles here. Okay, that's all. So this question is an easy question if you know how to write these 5 stages, and if you know how to think about it from the perspective of dependencies, and if you know what no forwarding means. Okay, if there was forwarding here, what happens? We have a question on that which we'll see just a few minutes later. Okay, so let's go to the next question now. Oh, so by the way, some people who may have forgotten how this works, there's a very nice page that I wanted to refer you to. So you can just Google search for this. You can just say pipelining. Just search for pipelining University of Washington. Okay, so let me show you. Pipelining University of Washington PDF. There is a very nice lecture slide from them. I think this is it. Yeah, I think this is the lecture slides. Is this it? One second. Their lecture slides are very good. So I just wanted to refer you to where is this? Okay, not this, probably the other one. So there is a pipelining one. Yes. So yeah, so this is a very nice lecture series which very crisply and precisely explains what happens in each of the stages. It says what happens in fetch, what happens in decode, what happens in execute, memory access, and write back. It clearly explains this. So I thought I'll refer you to this. Again, if you're not a course registered student, this is a great place. Of course, we explain all this in the course in a lot of detail, but this is a nice reference in case you want to quickly revise what all things happen in fetch, decode, execute, memory access, and write back. Right? So cool. Let's go to the next question now. Again, I've given the additional reference because I know people will be confused on what happens in which stage. So please refer to this very nice notes that I referred you to. Again, you can also download our publicly available notes for Gate where we explain this. This is a simple question actually, but questions like these have been asked for in Gate. The previous question is little lengthy. Don't skip it. If you're comfortable with pipelining concepts, answer it right away, because lengthy questions tend to be easy in Gate typically. Okay, I see people putting in the answers. Oh, for the next question, people are already putting in the answers. Okay. Did I make a mistake somewhere? Okay, let's see. Let's go with this. I hope you're putting an answer for the 5th question, right? A non-pipeline system takes 40 nanoseconds to process. Okay, I see a lot of the students putting in C as the answer. Some people putting in B. Okay. Let's see. Maybe I made a mistake when I was solving it. That's okay. Let's see the solution. Okay, I am getting a slightly different answer. So let's solve this. Okay, cool. So let's actually solve this question, right? So the fifth question here. A non-pipelined system takes 40 nanoseconds to process a whole task. Okay, very good. The same task can be processed in a 5-segment pipeline with a clock cycle of 15 nanoseconds. Determine the speed up ratio of the pipeline for 200 tasks. Okay, first let's write down for non-pipelined. So first let's write down for non-pipelined processor, right? What is the total time to finish 200 tasks? Each task take 40 nanoseconds. There are 200 tasks, right? So 40 into 200. This is 8000 nanoseconds for the non-pipelined processor. For the pipeline processor, what happens now? Look at this. For the pipeline processor, what happens? It says it's a 5-segment pipeline. So simple. Okay. If you have a 5-segment pipeline, how does it look like? Right. So you have 5-segment pipeline, right? So let's just see. So you have 5-segment pipelines like this, right? So on and so forth. Okay. So stage 1, stage 2, stage 3, stage 4, stage 5 for instruction 1, right? So let's assume the overlap is not a problem. There are no dependencies of whatsoever. So in this case, what happens now? So for the second one, so here it says you have 40 nanoseconds and you have 200 tasks that you want to perform, right? So the second ones, first stage, second stage, third stage, fourth stage, and fifth stage can be done now, right? For the second task, this is task 1, task 2. For task 3, 1, 2, 3, 4, 5 can be done here. For task 4, 1, 2, 3, 4, 5 can be done here. So imagine if you had 3 tasks, right? So imagine if you had 3 tasks, how much do you need if you had, let's, because it says 200 tasks, right? First, let's try to come up with a formulation. If you had 3 tasks, okay, this 5, okay, this 5 plus 3 minus 1. This is the number of cycles that you need, right? Look at this. For 3 tasks, you need 1, 2, 3, 4, 5, 6, 7 cycles, right? For 3 tasks, you needed 7 cycles. Okay. For 4 tasks, how many cycles do you need? 1, 2, 3, 4, 5, 6, 7, 8. So it is basically 5 plus 4 minus 1. Right? So if you have k tasks, because it's a 5 pipeline system, if you have k tasks, this is 5 plus k minus 1. Right? These are the number of cycles that you need. So we have 200 tasks here. So 5 plus 200 minus 1. Right? So these many cycles do we need? Okay, so let me use a calculator here just to be sure. So this is 205 minus 1, so that is 204. That much I can calculate manually. Okay. So 204 into 15 nanoseconds. Each cycle takes 15 nanoseconds. So 204 into 15. What is 204 into 15? Sorry, let me just go here. It is 204 into 15 is 3060, right? So this is 3060. Cool. So what is the speed up now? 8000 by 3060. So what is the answer here? 8000 by, okay, let me write it here. So this is 8000 by 3060, which will give us 2.61. So C is the right answer. Yes, C is the right answer here. Okay, cool. Most of you got it right, right? So the answer is C. So I did a small mistake while I was solving it earlier. I made the answer as B because I didn't use the calculator and I was trying to do it by hand. So the lesson learned for me is always use the calculator. I try to solve problems without the calculator sometimes and I make mistakes. So when I was solving it before this, I got B as the answer. But thankfully, I got corrected because a lot of you gave the right answer here. The answer is 2.61. I should just use a calculator to be careful. That's it. Okay, cool. So this is a simple problem actually. Okay, so let's go to the 6th question now. This is also easy actually. This is just about horizontal encoding and vertical encoding. If you know what those are, of course, we're talking about micro instruction encoding. If you know what those are, this is trivial. This is actually a trivial question. We just put in so that if somebody is not thoroughly prepared, they can still answer it. This is fairly simple concept. The horizontal coding and vertical coding is fairly straightforward. Yeah, I see a flood of answers. So this is trivial question. Anybody who knows these concepts can trivially answer this. Okay, yeah, so the answer is C. It's very simple. So what is horizontal micro instruction coding? Basically, this is a decoded format, which means one bit is connected to each control word, right? So you need 129 bits here, right? On the other hand, if you have vertical micro instruction encoding, everything is encoded in binary here. So if you have 129 control signals, you will need 129 log 2 and seal of this. So log 129 is just log 129 base 2 is just 7 point something. So the seal of it is 8. So the answer is 129,8. So if you know what is horizontal micro instruction encoding and vertical micro instruction encoding, this is a straightforward concept, right? Cool. Okay, so let's go to the next question now. This is a slightly lengthy question like the previous one, but please read this carefully. This is slightly lengthy, but that's okay. Please take your time and let's solve this step by step. This is also slightly lengthy and tricky. This question is lengthy, but similar questions have been asked in the past for GATE for 2 marks. So please be patient here, solve it carefully, you will get it. These questions are lengthy, not hard. If you just understand each of the stages of pipelining, this is simple to answer. Again, most problems in COA can be solved by drawing diagrams. Many students don't do that, which is why they struggle when they have to solve problems in COA. You have to draw diagrams. I think that's true for almost all the concepts in computer science. Diagrams are the easiest ways to make sure that you're not making mistakes. This is lengthy, but that's okay. Take your time. Please be cautious. Again, if you want, I'll point you to something. This has forwarding. Remember, this has forwarding, unlike the previous one. Unlike the previous example, this has forwarding. So please be careful here. Same standard 5-stage pipeline, but it has forwarding. I'm repeating that again. Everything can change if you say operand, this whole system has forwarding or not. The whole answer can change. So please be careful about it. Okay, I see a set of answers, 12, 11, 10, but let's give others some time. Again, there is forwarding here. That's the key. Please don't ignore that. For problems like these, it's okay to take time. If you know the concept, you'll easily get 2 marks here. Again, somebody is asking a question about question 4. It is hard and unfair to other students who are solving this problem for me to go back to question 4. Please email us if you have a question. If you're not clear with the explanation, please email us. One of our mentors will answer your question specifically. I see a question here, but I can't go back to question 4 now because that will just disturb the whole flow. Okay. So anybody who thinks that the answer may be incorrect or there is something that is missing or you're not sure, please email us. We will certainly answer all emails related to these topics, especially if there is something that you did not understand in an explanation of a live session like this. It's already 7:45. Okay. Okay, a good chunk of you have answered it. So let me go ahead and show you the solution. Again, my team helped me draw this whole diagram. So let's go through each of these instructions now. Right? So the answer is 10, not 11. Even though there is 11, this is not needed. So the answer here is 10. Okay. So let's go step by step. We have instruction 1, 2, 3, 4, 5. Instruction 1, the 5 stages are here. Now let's go to instruction 2. Look at this. In instruction 2, this is dependent on this. Right? This is dependent on this, right? And this you're getting it from memory. Remember, this you're going to get it from memory, right? So instruction 2's fetch will happen immediately. Look at this, instruction 2's fetch will happen. But after you do the memory, after you obtain the data from the memory, because there is operand forwarding, you can directly obtain it here, right? So you can complete the I2's instruction decode phase, right? The fetch phase you can do it right here for I2. I2's decode you can do it along with this because this is being fetched from memory and there is operand forwarding, right? So that's important. Now then you have EMW, right? Execute, memory operation, and then write back, right? Now let's see I3. Okay, I3's fetch will happen here, decode will happen here. But if you notice, I3 also depends on $2. Look at this. One of the operands of I3 is $2. $2 is dependent on this. But here it clearly says that this architecture allows forwarding. So I can execute it here because as soon as I2, remember I2 is already executed. See, I2 has executed, which means in $2, the result is already there of the end operation between $3 and $2. It already executed. Because there is forwarding, I can execute my instruction here because, look at this, because of forwarding, right? Remember the two things here. By the time I come here for my instruction 3, instruction 2 has executed, which means the resultant of this add operation is already there in this. Because there is forwarding, I have all my operands here. So I can execute here without having to wait. Okay, this is important. These two relationship is also very important here. Rest everything is straightforward. Again, the forwarding is the important concept here. That's why I've also stressed that. I4, you just write FDEMW. I5, just write FDEMW. Now, if you start counting, you get the number of cycles required as 10. So in this question, the most important aspect is all about the forwarding part. It clearly says that it has forwarding. Okay, in the previous question, it clearly said that there is no forwarding, right? Those are the two important things that you have to be careful about. Again, the reason we have given 2 questions like this in one session is because questions like this are asked in GATE, typically for 2 marks, and they're very scoring if you're careful about it, right? So cool. Let's go to the next question now. Again, some of the questions that you're asking, our team is also answering them. Okay, so this is a medium question, fairly easy. People are solving it. Good, good, good. Okay, so let me explain the solution to this problem. So this is a fairly straightforward problem. As somebody was writing in the comment section, this is actually an aptitude problem, but most gate problems are simple aptitude problems if you know the theoretical concepts from computer science, right? So let's see. So let's assume you have a new computer B, right? So let's write down. So on your machine B or computer B, the CPU time, right, on B is 6 seconds. That's what it says. Let's write down all the facts that are given to us here, right? So let's write down everything. Now, the second thing that is given to us is the cycle count. Let's write down the cycle count for B is 1.2 times the cycle count of A, right? It is 1.2 times the cycle count of A. These are two facts given to us. Now, let's write down about A also. What is the CPU time of A? The CPU time of A is 10 seconds, right? That's what is given to us, right? So a program P on computer A executes in 10 seconds. That's what is given to us, right? What is the clock speed of A? The clock speed of A that is given to us is 100 megahertz, right? That's what is given to us, right? So clock rate on A or clock speed on A is 100 megahertz, right? Now this is your CPU time. What is the cycle count now? Let's try to get the cycle count on A, right? Look at this. It takes 10 seconds. In 1 second, we perform 100 million cycles. So in 10 seconds, how many cycles do we perform? So it is nothing but 10 into 100 million, 100 into 10 power 6, because million is 10 power 6, right? So this is 10 power 9 cycles, right? So to execute the program on A, it takes 10 power 9 cycles, first and foremost. Now, what is given to us? That the cycle count on B is 1.2 times the cycle count on A. So we got the cycle count on A to be 10.9, 10 power 9 cycles. The cycle count on B is 1.2 into 10 power 9 cycles, right? This is one. The CPU time here is 6 seconds. Now the question is all about what is the clock rate that you need on B. So what is the clock rate that you need on B? Right? So these many cycles, these are the total number of cycles that you have. These many cycles, you will get it in 6 seconds, right? These are the cycles that you need, and the program takes 6 seconds to complete, which means how many cycles will be there in 1 second? It is 1.2 into 10 power 9 by 6, right? This is nothing but 0.2 into 10 power 9 hertz. But the question says that the answer should be in megahertz, right? So if you have to write it in megahertz, this is nothing but 200 into 10 power 6 hertz. So this is 200 megahertz, right? Again, here information is given indirectly. All you have to do is just basic multiplication and division. That's all there is here. It says, as somebody pointed out, it's a simple aptitude problem, but you just have to understand that you have to understand what is cycle count, what is CPU time, what is clock's time, or what is clock speed. If you understand the terminology, this is a fairly straightforward problem. Okay, so let's go to the last problem of the day. This is a fairly simple problem. This is also a fairly simple, straightforward problem. If you understand the terminology, this is straightforward to solve. Guys, please focus on the problem solving aspects, because I don't require to crack gate this year. I've done it long back. Okay, you have to crack the exam. So it is better for you to focus on the problem at hand. This is a simple problem. Okay, most of you got it right. It's a fairly straightforward problem. Let's write down things from scratch, right? You're on a design team. The clock of the processor runs at 300 megahertz. So the clock speed, let's write down the facts here. The clock speed is 300 megahertz. And the hardware expert says that if you double the number of registers, so they're trying to double the number of registers, the cycle time must be increased by 10%, right? So if the clock speed is 300 megahertz, what is the clock cycle time, right? What is the clock cycle time? The clock cycle time is 1 by 300 mega, right? So what is this? 1 by 300 mega will be 3.33 nanoseconds, right? If you write it in nanoseconds, right? Now, what does it say? The new, so it says the new cycle time, because if you double the registers, the cycle time will be increased by 10%, right? Which means the new cycle time is 10% more than this. So multiplied by 1.10, 10% more than this. So this will give us 3.66 nanoseconds, right? This is what you get, right? Now, what is the new clock speed? If this is the new cycle time, what is the new clock speed? Right? The new clock speed is simply 1 by this, 1 by 3.66 into 10 power minus 9, right? So if you simplify this, you get 10 power 9 by 3.66. We want the answer in megahertz, right? So this is 1000 into 10 power 6 by 3.66. So let me just use a calculator to avoid any errors. Sorry, where is my, wait, it went into my calendar. Okay, 1 second. I don't use a calculator much, so calculator. Okay, got it. So 1000 by 3.66. 1000 by 3.66. This is 273, right? So the answer is 273 megahertz. This is the closest answer, right? So 273, this is mega, so 273 megahertz, right? So folks, again, for some of the questions today, you may be confused about the answer, but please feel free to email us, right? It is very hard to go into the details of every answer because we have problems and we wanted to finish all this in 1 hour. So it is sometimes hard to go into the theoretical concepts and explain something as if you're explaining it in a classroom. So you can check out our course videos for it. And our whole team is very proud of the content that we have created for COA. We believe it is one of the best contents that we have ever seen ourselves. So some of these concepts have been explained in a lot more detail. Remember, we can't spend 20 minutes solving a problem in a live session. If you had that, if we had that liberty, we could have done it better, right? But we don't have it because we want to solve about 9 to 10 problems in every live session. So if you want to understand some of these concepts, please revisit our content in the course videos or check out some of our free videos that are available, right? And anything that you think is incorrect, if there is something incorrect here, please let us know, and we will respond back to your emails and try to resolve as many as possible. Okay. Thank you very much, folks. Thank you. See you. See you the coming sorry. We have the next session on Saturday, right? On Saturday we have COA 3, right? So let's finish that on that day. Cool. Sounds good. Thank you very much, folks. Thank you for your time, and see you on the coming Saturday again at 7 p.m. Bye-bye.